As we go now into additional material that's included with Chapter 8. This used to be called 8.5, but here they're calling it Lesson A.2. We're in the Learn, and these will be our objectives. Evaluating logarithms using basic properties. Translate equations between exponential and logarithmic form. Use the definition of exponents and logarithmic functions to solve equations. To start us off, we want you to take a look at what I've set up here as background. Now, we're dealing with two forms. One is called the exponential form, and it looks like this: y equals b, which is your base, to the x power. Now, an example of this, and we'll go right to left. If our base is 2, and we raise it to the third power, our answer is 8. So, a little sequence here, kind of a flow chart, is we have our answer, and that came from a base raised to an exponent. So we'd like you to copy this into your notes, and you can pause as needed. Now, there's also, as we introduce, the logarithmic form, where we have a log, and by the way, the log is an exponent. And for instance, the log base 2 of the answer 8, the exponent is 3. Now, putting that into sort of a flow chart, we have log of a base, and the answer is equal to an exponent. So logs are exponents. And we had a lot of background on exponents back in Chapter 5. There's a lot of math here, and we'll go on to just introduce another term, and that is the inverse of something. Now, if we have this exponential form, y equals b to the x power, to get the inverse of it, we would say switch the x and the y. That is the inverse function of this. And what does this do? Well, I'm going to give you some more background information. Now, we'll take this in steps. Here is our exponential function, and we want you to pause and sketch this graph. But before we do, we're going to make a t-chart to get some values. Now, here's our x values, which again are exponents. What will our y value be if this equation is, let me write it over here, y equals 2 to the x power. Now our variable is the exponent, and our base is 2. So 2 to the 0 power is 1. Anything to the 0 power is 1. Now if x is 1, 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. Now, how about if the exponents are negative values? Well, we get 2 to the negative 1, that you may recall is 2 to the negative 1 over 1. We bring our exponent down to the denominator, and this becomes 2 to the first, something we had in chapter 5. So this becomes a 1/2. Now, 2 to the negative 2 becomes 1 over 2 to the second. We just bring our exponent down, and this is then 1/4. And 2 to the negative 3 becomes 1 over 2 to the third, bringing our exponent down. This becomes 1/8. And you'll notice that if it's a negative exponent compared to what you have here, all of these numbers are the reciprocal of this. Now, let's do the inverse, where we're switching around the letters. Your x goes where the y was, and the y goes where the x was. Now, interestingly, this is, when we're going to show you the graph, this is a general shape of what this graph would look like, and the general shape of what this graph would look like. And we can change the bases, and they have the general same shape. The values, of course, would be different. Now, what we're going to look for is that the exponential form and the logarithmic form are the inverse. So, what I've done, and take a moment to sketch this. Now, in your notes, you're going to sketch a graph that looks like this. Now, we had said, and then this is just a general form. The blue line is the general form of the exponential growth. The red line is the general form of the inverse of that logarithmic form. Okay. Now there's some key words that I want you to add to your vocabulary. Now keep in mind, when anything is 0 as an exponent, it is a 1. And we see that here and here. Now in its exponential form, if your value of x is a whole number in a sense, it moves along this direction. In the inverse form, it moves in this direction. Now over here on this negative side, you notice this line keeps getting smaller and smaller and smaller fractions as it gets closer and closer to the x-axis. Well, this x-axis has a special name. We want you to add it to your vocabulary now. That x-axis is called the horizontal asymptote. And you might say, what is an asymptote? Well, an asymptote is something that something else gets close to it, but it never reaches it. So this line on this side gets closer and closer and closer to 0, which is what the y value is at this point. And you recall from previous lessons that the horizontal line of the x-axis, the equation of it would be y equals 0. Remember, we did that in chapter 3. And since it's horizontal, it's called the horizontal asymptote. Now, as you plot the logarithmic form, the inverse of this, the line that gets closer and closer on this direction happens to be the y-axis. And if you recall, the y-axis is a vertical line, and the equation of that is x equals 0. So this vertical line, the y-axis, is called the vertical asymptote. So you want to get some of this data down, pausing and sketching. Now another thing that happens too, we have this dotted line. Now this dotted line, interestingly, if you were to fold this graph along this dotted line, the red line and blue line would be on top of each other. So there's a sort of symmetry here. And we call then this dotted line, the equation of which, interestingly, is y equals x, because there's a 1 there that we don't write. This is called the axis, and you're going to write this down, symmetry. Okay, hopefully you have an idea of the relationship, and this is all background. As an aside, I should have up in this upper right corner a little circle with an eye in it. And if you click on that, there is a short video that I did to illustrate exponential function and logarithmic function as being the inverse of another. You're not going to be tested on that, but just as knowledge of background information. Now let's go on to our first exercise. These are laid out, so we want to follow that exponential form, and this is example 1, and then move it to its logarithmic form. So this is just a little practice. Again, there's your base, there's your exponent, gives you the answer. So the base 2 exponent 3 gives you the answer 8. Now in its logarithmic form, the base will be 2. The answer we said was 8, and the exponent is 3. So going from exponential form to logarithmic form. That was A. Don't forget to put the letters, because there'll be hints on our quiz. And then just take a moment to copy these down. And again, if you were to do this, setting up these little boxes that I have here, kind of a good way to be able to easily transform from one kind to the other. And be so kind as to copy this into your notes as well. This is a good little tool here, that if you have a base to the 0 power, anything to the 0 power is 1. Now, if you had the log base b of 1, this is its exponential form, that's going to be 0. So copy this down too. Log base b, where 1 is the answer, we know that exponent is going to be 0. Now, if we had base of the first power, that is just going to be the base. So if we converted this to its logarithmic form, this would be log of the base. Now the answer is the base, that's going to be 1. So whenever we have this arrangement, as we'll see later on, that's always just going to be 1. All right, so examples, of course, are going to help with this. So let's go on. Now, below here, we have a summary of basic properties of logarithms. That is, b, the base, has to be greater than 0, and the base cannot be equal to 1. So we've done this one already. Log of base b, answer 1 is 0. Log of the base of a base is 1. And here, if we had something like this, x would be greater than 0. And then here, if we have a base of a base raised to the x power, it's just going to be x. Because this part we've said here, this part here is 1. So 1 to the x power is x. Again, some of this is a little technical, but on to our examples. All right, looking at our first example, this is example 2 now, part A. So we have log base 3 of 1. Now what would that equal? Well, we said if we put that in its exponential form, this is going to be, let's say this is going to be x here. This is, our base is 3, our exponent is x, and our answer is 1. Well, what did we say? Anything to what power is 1? And that would be 0. So this would be log base 3 of 1 is equal to 0. And that's what they're showing. Now, the second property, b, log base 8 of 8, that's going to equal something. What does it equal? Well, when he said when it was in this relationship, and if we put it in its logarithmic form, 8 to what power is 8? Well, 8 to the first power. So here, x is going to be 1. Earlier we said that in this case, when we have this, the answer is just what appears there. That is the 20. So all of this part is just 1. So 20 equals 20. And let's raise it up for our other part. Again, converting this part to its exponential form, 2 to what power is 32? Now, one of the other rules that we're not mentioning now, but is sometimes used, if we go 2 to the x, can we make this base into a power of 2? Yes, that would be 2 to the 5th power. 2 to the 5th power is 32. So if our bases are the same, then our exponents have to equal each other. And that's where we get the answer of 5. Now for letter E, and they are showing the solution, but converting it to its exponential form, we see x to the 10th equals 0.01. But if we put this 0.01 into its regular fractional form, we realize then that this x has to be some negative exponent. And this is 1 over 10 to the second. So this would have to be x equals a negative 2, which is what they're showing here. Okay. In example 3, they're asking us to do some logarithmic equations. So again, copying this down, log base 16 of x equals the exponent 3/4. So we've put that in its exponential form. That'll be our base to the 3/4 power equals x. Now, from our study of radicals, this gets converted to the radical form. Our base, our radicand is 16. Our index number is going to be 4, and this is going to be raised to the 3rd power, and that will give us x. Now, the 4th root of 16 is 2, so 2 to the 3rd power is 8, and that's where we get our answer. They're doing it a little different way. I like it this way. Let's go on. Now for example 4, be sure to note the example numbers. Log base 4 of 8. The exponent is x. We're going to convert it to its exponential form. So 4 to the x power is 8. So if we were going to use that technique of getting our bases the same, this could be 2 to the 2nd to the x power equals 2 to the 3rd, which is 8. But notice what they're doing here. We multiply this, so in a sense this is 2, multiplying our exponents using the powers rule. This is 2x. That's better. Equals 2 to the 3rd. Now our bases are the same. We get 2x equals 3. X equals 3/2. This one was a little more challenging here. All right. So as we sort of summarize now our logarithmic functions and exponential functions as a review and for closure, we go back to the actual graph of y equals, I should say not x, but 2 to the x power. And these are the points that we got. And the logarithmic form, the inverse of that, is this. Y equals log base 2 of x. And there's our axis of symmetry. There's our horizontal asymptote. There's our vertical asymptote. And in a sense, a nice way to finish up this particular lesson. We've asked you to do lots of graphing in this section, and I would ask you to add this picture too. So again, you're just making a little sketch here, and I'll show you what it's like. So again, if x is 0, it always goes through 1. But if your base is 10, notice if it was 2, it went through there, and then there, went out this way. But if your base is larger, the curve gets closer to the y-axis, and we see it in its inverse logarithmic form here as well. And I think that's what they're showing. So just, again, everything stays the same, but this gets so much closer as opposed to when it looked like this. This was a 2, then a 3, and a 4, and a 5, and then 10 would look like this. Now, I do have a homework help for this, and if you need that, of course, that will be available. And for background, if you want to check out that supplemental video on the inverse.